It's a great pleasure and honor to welcome Professor Eric Priest to the colloquia, the ISC. Professor Priest, Eric, is one of the best known, most famous solar physicists at present. And he did his PhD thesis with Thomas Cowling, which is one of the legendary names in MHD theory in Leeds. And then his extremely successful scientific career is taking place in the University of St. Andrews, where he obtained his first professorship in 1983, I think. Is that right? And so if people who like the ideas may want to look up the number of citations of his paper, he has got a staggering more than 11,000 citations to his publications, which is just out of this world, an incredible number. So his career he's received a number of prizes and medals, like a photosphere, the Hale Prize of the American Astronomical Society, the gold medal of the Royal Astronomical Society, the Penka-Pushkin medal, etc. He's a fellow of the Royal Society, which is the oldest academy of sciences in the world. The Royal Astronomical Society, the Royal Society of Edinburgh, the Norwegian Academy of Sciences, etc. So we are extremely pleased that he's going to talk today about the magnetic nature of our sun. So.
Thank you, Fernando. You're always very kind. It's a real pleasure for me to visit the best astronomical institute in Europe, which contains one of the two best solar physics groups in the world. You may wonder what the other one is. You can you can debate amongst yourselves. I'll be here all day today and tomorrow, so I'd love to speak with many of you about your research. So what I plan to do is very simple, just to compare what we knew about the sun in the 1960s. Here is an eclipse of the sun in 1966, and what we know about the sun today. I bring you greetings from St. Andrews. There it is on a beautiful day, but probably colder than it is here. Golf was founded in St. Andrews. And also, historically, it was the ecclesiastical centre of Scotland. There's a ruined cathedral and a ruined castle. And also, the university was founded there in 1413, so it's the third oldest university in the UK, the oldest one in Scotland, and one of our latest graduates was Prince William and Kate as well. And it was great fun meeting them on lots of occasions. But I'm a mathematician, so why does a mathematician study the sun, you may wonder? Well, the answer is very simple. Mathematics is a language for understanding what's going on in various physical phenomena. James Gregory, for example, I happen to be the James Gregory Professor in St. Andrews, and he was the first professor of mathematics in St. Andrews in the 17th century. He was one of the co-founders of calculus with Newton and Leibniz. And for example, he discovered Taylor series 40 years before Taylor. He was the first person to be able to integrate by parts or to change the variable in integration. He did lots of things that we just take for granted in calculus every day. And he taught calculus in St. Andrews 100 years before it was taught in Cambridge. But also, he invented the Gregorian telescope. In addition to that, he discovered the diffraction grating. He was walking along the beach in St. Andrews one day, and he picked up a seagull's feather, took it back to his laboratory and shone a light through it and saw this beautiful diffraction pattern, and then wrote a letter the next day to Isaac Newton and said, I wonder, Mr. Newton, have you seen this phenomenon that I've just discovered? So he did many great things, but unfortunately he died at the age of 37, and it's partly because he died so young that many people don't know of the important things that he did. Here's a painting of him in his laboratory in St Andrews. You can go into that laboratory today and you will see on the floor one of the first astronomical meridian lines that he laid down many years before Greenwich. And also on the wall is the first clock that was able to time to fractions of a second. He had it especially designed. So he was a very great man. I thought I would just summarize a little bit of history, just as an introduction. Tenerife, you'll remember probably that the first telescope was installed on Teide in 1964. The Institute, he was founded in 1975. My own personal history, I started my PhD in 1966, and that's why I'm choosing this year as the comparison. 2 years later, I had a permanent position in St Andrews, a tenured position. So I was very fortunate, and things were a little different in those days from what they are today. Then in 1981, I wrote a book called Solar MHD. But since then, both observation and MHD theory have been transformed. And so I'm completely rewriting that book and hope to have it finished in 2 or 3 months. So if anybody wants to have a look through any of the draft chapters and help check them for me, I'd be delighted. So the question is, what are the major discoveries that we've made about the sun since the 1960s? Have we solved the main questions about the sun or not? So I'm going to look back and compare with the present. These are the MHD equations that we knew about in those days. The MHD equations haven't changed at all. They're the same equations. But what we've deduced from them is incredible. The difficulties of these equations are that they're nonlinear, that we have a wide range of scales, and that the magnetic fields are extremely complex. And so we need complementary approach of computational experiments, of analytical theory that is guided by clever physical insight. And also we need the theories to be inspired by observations. If as theorists we're not inspired by the observations, the detailed observations, then we can dream and we can just go along nonsensical routes. So we need to be very closely allied with the observations, and I think this is really one of the great strengths that you have here in Tenerife. So first of all, basic MHD theory. In 1966, it was relatively simple. As far as the equilibria were concerned, we just talked about potential equilibria, potential fields. As far as waves are concerned, we talked about waves in uniform media. And reconnection, we knew about reconnection at an X point in 2 dimensions. Petchek's theory had just been proposed, and the tearing mode instability had just been proposed as well. Now, in those days, it was a very small part of solar physics, but now it plays a central role in our subject. As far as equilibria are concerned, we're focusing on nonlinear force-free fields and their properties. We know very little in general about the properties of nonlinear force-free fields so far. And we're also focusing on the nature of complex topology. As far as waves are concerned, a lot of the work has gone into 2-dimensional non-uniform equilibrium, the waves in those structures. And some work has gone into nonlinear wave motions. Reconnection, we're now working on 3-dimensional reconnection, which can take place in several locations. It can take place at null points, where the magnetic field vanishes. It can take place at separators, and it can also take place at quasi-separatrix layers. So what are these animals that I'm talking about? Well, first of all, in 2 dimensions, if you have 4 sunspots in a row, with their polarities alternating, you'll find that up above the photosphere there will be an X point where the magnetic field vanishes, and the magnetic fields that come from or to that X point will be very special magnetic field lines. They're called separatrix curves, and they separate the two-dimensional domain into topologically distinct regions, in the sense that all the magnetic fields in field lines in a particular domain will just start at one particular source and end up at another sink. What that means is that as you cross a separatrix, the mapping of the field lines from one foot point to the other will be discontinuous. There will be a sudden jump in that mapping, because when you're to the right of this separatrix, all the field lines will map to there. When you're to the left, they will map right over to here instead. Let's see, I just want to check that this pointer is working. Yes, there we go. So that's what happens in 2 dimensions. In 3 and the foot point mapping is discontinuous there. In 3 dimensions, it's very similar. The separatrix curves become separatrix surfaces that separate the 3-dimensional domain into topologically distinct regions. So if you have 4 sunspots on the plane, all the magnetic field lines below this separatrix surface, this dome, will go from that positive sunspot to that negative sunspot. All the ones above will go from this positive sunspot over to this negative sunspot. And in this particular case, you've got 2 domes of magnetic field lines, and they intersect in a curve. And that curve is also a magnetic field line. It's a very special field line. It's called a separator. And it's special because when you move the sources around, current sheets tend to form naturally along the separator. And so that's where reconnection naturally tends to take place. It turns out that reconnection can also occur at things called quasi-separatrix surfaces. And those are surfaces where the mapping has a gradient which is large, but is not infinite. There's not a discontinuity in the mapping. There's a sudden change in the mapping. But essentially the same processes of current sheet formation and reconnection can take place at these quasi-separatrix layers. Now, I could spend the whole lecture talking about this topic, but I'll resist that temptation. As far as basic MHD is concerned, where will the developments be in future? Well, I think for equilibria, we will start looking much more at non-force-free equilibria, which are very important if we want to link down properly to the solar surface. We'll be discovering the properties of waves in genuine 3D equilibria. Very little has been done on that so far. And as far as reconnection is concerned, we'll be determining the rates of reconnection in the different regimes of reconnection that we now know exist in 3 dimensions. And we'll be focusing on working out what are the observable consequences of these different 3-dimensional reconnection regimes. And as well, introducing non-fluid MHD effects will be very important. Okay, so now let's look at the different parts of the solar atmosphere in turn. First of all, the interior. In 1966, we'd calculated the temperature structure as a function of radius in the interior of the sun, purely based on theory. Local 5-minute oscillations had just been discovered by Leighton, and so had supergranulation. But it was not until 1970 that Ulrich suggested that these 5-minute oscillations were in fact global modes, that they were standing internal sound waves in the sun. And they were not observed for the first time until 1979. as far as the dynamo is concerned, it was thought that it was generated throughout the whole convection zone. Tubes had been suggested by Parker to rise by magnetic buoyancy, and that whole process is now discussed in very much more detail with a magnificent series of numerical experiments that have been conducted by Fernando Moreno and his colleagues. And here you can see him appropriately for a Tenerife researcher with the beach in the background. So, but also in 1966, we had in mind the fact that Parker had suggested that you could generate a poloidal magnetic field. You could turn a poloidal magnetic field into a toroidal magnetic field by differential rotation. And then you could turn the toroidal magnetic field back into poloidal magnetic field by turbulent cyclonic convection. Parker had made this suggestion, and then later on it was formalized as mean field theory. And it was realized from the theory that you needed the angular velocity of the sun to decrease as you moved outwards. Its gradient had to be negative if you were going to get migration of the dynamo towards the equator as the solar cycle process proceeded. Now, in the 1980s, problems with this picture began to arise. First of all, it was realized from the properties of the magnetic field at the surface that you needed fields down in the convection zone of 100,000 Gauss. Those would rise very quickly, and they would also be resistant to turbulence. So that was a problem for the theory. Helioseismology also showed us that the angular velocity was not decreasing with radius, but was constant. So that was another worry. There were also doubts about the validity of turbulent diffusion and the alpha effect. But then in the 1990s, two suggestions were put forward. The first was that the toroidal magnetic field could be converted into poloidal magnetic field, not throughout the whole convection zone, but in the tachocline, the shear layer at the base of the convection zone, and that the dynamo could then be working there. Or alternatively, it was suggested that it could be working near the solar surface in a so-called flux transport dynamo. These were the two suggestions that were put forward in the 1990s. So what about the future? Well, I think we need clearly more constraints from helioseismology. We need more observations to guide us about what's really happening with the dynamo. We need really to reassess properly mean field theory. And we also need to develop realistic tachocline and flux transport dynamo models. Both of those types of models are very crude at the moment, so we need to improve them and make them more realistic so that we have a better chance of being able to predict the solar cycle, for example. The predictions are notoriously bad at the moment. So that's the interior of the sun. Let's turn to the photosphere itself. In 1966, there was no magnetic field outside active regions. Right? And I actually shared an office in 1971 with Jan Stenflo. And he said to me, well, I've just come up with these observations and this theory, and I really think that there are magnetic fields of 1,000 Gauss in the quiet sun in small regions. And I just laughed at him. I thought he was absolutely crazy. I thought that was completely impossible. So it just shows you have to be careful when somebody tells you an idea that sounds crazy. It may turn out to be right. In the 1980s and 1990s, the picture outside active regions was that the magnetic field is vertical in the photosphere, and that it's located mainly at the edges of supergranules. And so as it comes through the surface, it then spreads out and fills the chromosphere and corona. This was the picture we had in the 1980s and 1990s. But then Hinaday came along. Bruce Lights had previously had a really important paper in 1996, I think it was. But most people had overlooked that paper. Valentin was one of the co-authors, he was reminding me yesterday. And what Hinaday showed was that the picture really depends on the threshold for the magnetic field. If the magnetic field threshold is set at 500 Gauss, then indeed you do see the supergranules being, the magnetic field being concentrated at the supergranules. But as you lower the threshold, you see more flux. Above 100 Gauss, this is what it looks like. Above 25 Gauss, this is what it looks like. So in other words, the interior of the supergranule cells is filled with magnetic flux, and that vertical flux is being concentrated, is being located between granules rather than between supergranules. So what that means, the implication of that is that the chromospheric and coronal magnetic field is incredibly more complicated than we thought it was before. Another big surprise was that Ryoko there likes Guinness for a start. She's holding clasping there a nice glass of Guinness. I thought it was only Irishmen that liked Guinness, but anyway. But anyway, Hinaday also found these horizontal fields that also Bruce Lights knew about in 1996. And these are located then at the edges of the granules. What that means is that, whoops, come on, don't go, what's going on? Hey. Also, these horizontal fields mean that you have many small magnetic loops of flux that are emerging in the internetwork as part of the internetwork flux, and then spreading out, filling the chromosphere, and closing down very low down, many of them, but some of them higher up. And Marian produced this really nice paper in 2007 about that, and Valentin and colleagues obviously showed this in very much greater detail with Sunrise. Sunrise has just been fantastic, hasn't it? I'm so excited about all the discoveries, and you've been playing a really large part in these discoveries here. You've resolved the kilogauss fields. The flux is lower by a factor of 10 than it was before, the flux that we could detect. There are 10 times more features in Sunrise than seen in Hinaday. And also the results, I think, about acoustic waves and about the fact that the weak magnetic fields are oscillating with the granular period. I think those are really fascinating results, which I'd like to learn more about. And there are many more observations, I know, results that you've been involved in. Those are just some of them. Sunspots too. Here are some of the amazing images that came from the Swedish Solar Telescope on La Palma, and which we now routinely see with Hinaday and SDO. And up in the chromosphere as well, these amazing magnetic structures. It's a magnetic world that we have there, continually evolving. And the fact that we can also detect the magnetic field in the penumbra, and we see this kind of comb-like structure. There's a recent paper which some of you may know about. Until recently, I'll say about that in a second. Until recently, the penumbra was, of course, a mystery, but I think a big breakthrough was this numerical model of Matthias Rempel. It's incredibly realistic looking, the sunspot he has. And what I really like about his approach is that he hasn't just said, this is the result of my numerical experiment, this is a sunspot. He's then gone and spent much more time analyzing in detail the nature of what's going on there, asking physical questions and trying to understand why the structure is looking like it is. That is much more important than just producing that image that looks realistic. He's understanding the physics of what's going on there. And he then claims that everything you see in the penumbra is just a natural result of convection in an inclined magnetic field. So this other paper that some of you may know about, I think, is really interesting, by the group, one of Solanke's little subgroups in Lindau, where they've analyzed Hinode SOT data of a sunspot, and they claim that all the penumbral filaments are similar, regardless of their location within the penumbra. They lie between dark lanes with more vertical field, as we knew before. But what they do is to pick out individual filaments in velocity, in magnetic inclination, and in temperature. And they study dozens of them and try and come up with their mean properties. Schematically, what they find is that there is a bright head of each filament near the umbra, that there's then a flat central portion where you can see clearly the Evershed flow, and there's a dark tail. So as an example, with velocity, inclination, and temperature, this is what they find. In the head, the upflow is typically 5 kilometers a second. The field is between 1.5 and 2 kilogauss. And the temperature is hotter than the surroundings. It's about 6,600 degrees. In this flat central section, the magnetic field is horizontal and the flow is horizontal as well. The field is about 1 kilogauss. And then in the tail, there is a downflow of about 7 kilometers a second. The field is stronger, 2 to 3.5 kilogauss, and it's cooler than the surroundings at about 6,000 degrees. And of course, similar features have been found in various papers that several of you have been working on over the last few years. But I think this work, together with the Rempel work, really is a major advance in our understanding of what's going on in the penumbra. In future, though, what I would like to know about the photospheric magnetic field, and I think, many of you can probably answer these questions for me over the next few years. For the quiet sun, I would really like to know how much magnetic flux there is inside the supergranule compared with on the network. We used to think only 5% or 10% of the flux was inside the supergranule. And then Sami said to me, no, he thinks it's about 50%. But now, is it 90%, 95%, 99%? What is the answer to that? And how does it vary from the quietest parts of the sun to more magnetic regions? What is the ultimate size of a photospheric flux tube? My guess on theoretical grounds would be about 10 kilometers, but I may be completely wrong. And what is the effect of this very complex magnetic carpet on the coronal heating, on irradiance as well, and also on the overlying chromospheric and coronal magnetic field? I think these are very important questions. As far as sunspots are concerned, certainly as far as the Rempel calculation is concerned, the outer penumbra is certainly not realistic. There's not a good understanding yet of the outer penumbra. So I would like to understand that better, and I still would like to understand Evershed and mote flow better than I do at the moment. In addition, of course, from helioseismology, we need better estimates than we have at the moment of the sub-photospheric structure of sunspots. What's really going on down below the surface of a sunspot? Laurent Gizon from Lindau and his group have produced reasonably good estimates, but I don't think it's yet the final word on that topic, because there's a real problem in inverting when you're going through a magnetic structure. My next topic would be prominences. In 1966, we had the Kippen-Einschluter model of a prominence of normal polarity. Now we know that most prominences are located in magnetic flux ropes of inverse polarity. And we know about the barbs, which show the chirality of a prominence. Hinaday has shown incredibly fine threads and complex flows within prominences, which to me are still a great mystery. But I think a major advance is this model by Lanier and Desmoulins, their flux rope model, in which they suggest that overall you have a force-free flux rope with the barbs being plasma that is suspended in dips that are near parasitic polarities. They're above parasitic polarities in the photosphere. And so this is a comparison of a filament picture taken on Tenerife with their model. The comparison, I think, is very good. So I think this model is a major advance. Another important model that has recently been proposed talks about the evolution of the global coronal magnetic field through a series of nonlinear force-free fields in response to motions of the photosphere, global motions of the photosphere, in response to flux emergence, to diffusion of the magnetic field across the solar surface, to meridional flow, and to differential rotation. And the remarkable thing about these models is that they are able to predict with 90% accuracy the locations of prominences, of all the prominences that are outside active regions, quiescent prominences. And they also are able to predict the eruptions of many of the coronal mass ejections that we see. So I think this model too is a very important advance. There are real problems with constructing nonlinear force-free fields in general, but I think this is a very promising way to go, because there are an infinite number. If you give me just a snapshot, of the magnetic field, there are an infinite number of magnetic fields. You can't produce a nonlinear force-free field that matches all the magnetic field observations when you've got the transverse field as well. You have to do the best you can, but it's only an approximation to what's happening. So there are real problems I think Thomas Wiegelmann is doing a wonderful job in Lindau. He has the best approach in the world, as far as I'm concerned, for constructing these nonlinear force-free fields. But there really is a difficulty, and I think this alternative way of seeking the evolution in response to observed motions in the photosphere through nonlinear force-free fields is a very good one. In future, I would love to know more about fibril structure and the nature of the flows and the waves in prominences. What is causing the fibril structure? We have no idea. What is causing the flows that we see in prominences? Again, we have no idea at the moment. So I think this is a very important direction to be going along. Coronal heating. Well, in 1966, for the corona, we had one image per year. And we waited eagerly to see that image, to see what the corona looked like that year. Can you imagine that? The corona was heated by sound waves in 1966. Now we see the corona direct in X-rays and in EUV, and we have a continuous stream of images of the corona. We're so fortunate. Do we realize how fortunate we are? We see coronal holes, coronal loops, X-ray bright points. We realize now that the corona is heated somehow by the magnetic field. nanoflare reconnection, this braiding model of Parker, was for many years the standard model for heating the corona. And now this has been updated and superseded by the coronal tectonics model, which is a refinement of Parker's braiding model and is much more efficient, much more effective than his model. The idea here is that each coronal loop that you observe, in fact, consists of many magnetic strands which link down to the surface in many different magnetic sources. And the magnetic field from each of these sources is separated from each other by separatrix surfaces. So as the sources move, these small magnetic fragments move in the photosphere around, that will generate currents along the separatrix surfaces that are separating the flux coming from each of these magnetic fragments. So what that means is that the chromosphere and corona are filled with myriads of current sheets that are continually forming and dissipating and heating the atmosphere impulsively on small scales. This is the picture that we have now of the way the corona is heated. Also, an interesting calculation, I think, that was done with SOHO MDI was to construct the magnetic field lines on the basis of the photospheric magnetic field, just to construct potential fields. And what they found was that each magnetic source that they saw in MDI, on average, was connected to 8 other sources. So that gives you an idea of the complexity of the magnetic field just from MDI. And then they worked out the statistical properties of those magnetic field lines. This is just potential field extrapolation, which is very valuable and I think is much more useful than linear force-free fields. I think there are we can talk about this later, but I think there are real problems with linear force-free fields. I would prefer either to do potential fields or non-linear force-free fields, really. But what they found then, from the statistical properties, they could work out, how much of the flux closed down at different heights. And so 50% of the flux in this calculation closed down below 2.5 megameters, and so on, and 90 to 95% below 25 megameters. What they also did, though, was to follow the magnetic fragments in the magnetogram. They labeled each magnetic fragment, and they followed them in time, and then they recalculated the potential field at each time. And they asked, how long does it take for all the field lines in the corona to reconnect? And they found that was only 1.5 hours. So there's an incredible amount of reconnection going on continually in the corona. Now, this was on the basis just of poor old SOHO MDI magnetograms. I would love to see this very simple calculation redone for sunrise, for example, or for Hinaday. That's provided you could follow enough of the magnetic fragments in time. It's quite difficult to track them, isn't it? But if we could do that, it would be really interesting to know, just what are the statistical properties of the field lines from more modern instruments than MDI, and what is the reconnection time as well. A recent discovery, an important discovery, was about spicules. Previously, we knew about normal, so-called type 1 spicules, which had velocities of 10 to 50 kilometers a second. They reached heights of 3 to 5 megameters, and they lasted between 3 and 10 minutes. But now, Bart Dapontier and his merry gang have, very merry most of the time, have come up with this observational result that there are also type 2 spicules, which are much faster. They reach higher altitudes, and they're much shorter in time. And in the movie there, you can see that they're like prairie grass, swaying to and fro in the wind. And the interesting feature of these is that they heat to transition region and coronal temperatures as they fade away in time, whereas the type 1 spicules, most of them go up and then fall back down. So the obvious question is, how much of a contribution do these type 2 spicules give to coronal heating, and how much to accelerating the solar wind? So far, the estimates, in my view, are just back of the envelope. I think that this question needs to be addressed in much more detail in future. From SDO, we now know that coronal loops consist of multithermal strands, subtelescopic multithermal strands. And an interesting result is that they've shown that each strand tends to be reheated after about 100 seconds and that's before it has chance to cool back down. There are lots more observations from results from SDO as well, but as far as coronal heating is concerned, in future, what I would like to see addressed is a really in-depth comparison between waves and reconnection. You see, both waves and reconnection are clearly important in the corona. They're both occurring. But at the moment, you tend to have people who either have wave spectacles on or have reconnection spectacles on. So they only view things from a wave viewpoint or from a reconnection viewpoint. What we need is a proper in-depth comparison of the relative contributions, both in the chromosphere, in active regions, in X-ray bright points, in the so-called quiet sun. I don't think any of the sun is quiet anymore, but you know what I mean by it. We need to compare the different possible mechanisms in these different regions. It's possible that you will have different ones dominant in different parts of the sun. I think it's likely, for example, that reconnection in active regions is very different from, heating in active regions is very different from heating in the high corona. I think it's quite likely that it's different. We need detailed numerical experiments on coronal tectonics. Very little in theory has been done on this so far. I would like to understand, Javier, much better the nature of the transition region. Maybe you understand it completely now, but I don't, and I would like to understand. I mean, to me, what is the transition region? It's all the plasma that happens to be heating up through 10 to the 5 degrees or cooling down through 10 to the 5 degrees. I mean, we know for sure that the corona is not static, that the atmosphere is not static. The plasma is continually being heated up and cooling down all the time. And the plasma that just happens to be at 10 to the 5 is what will be emitting in transition region lines. But I would love to understand much better the nature of that transition region. I would like to understand better the cause of spicules and of fibrils and of jets that you see both in the photosphere now, Valentin was telling me, and Carlos, but also the jets that you see in the chromosphere and the corona, the X-ray jets. Are there different causes? And I think here numerical experiments will be very important, and so will observations. But we need numerical experiments that are not you don't just fling the equations on the computer and do what you like with them. You have to very carefully design them to answer specific physical questions, I think. Also, I think it's going to be very important to go beyond single fluid MHD in the way that some of you, I know, are beginning to. The solar wind. Well, in 1966, we had simple Parker models of the solar wind. The velocity was just it was a spherically symmetric expansion. The velocity was a function of r. We were very happy with those models. Then in the 1970s and 80s, coronal hole models were developed, very simple coronal hole models. In the 90s and noughties, Soho came along and observed the outflow in coronal holes for the first time, low down, and also this intriguing observation by UVCS that there are very large perpendicular temperatures and velocities for the minor ions, which is suggesting to me that there's some kind of ion cyclotron resonance going on there. But the details of that have not really been worked out properly yet. Then Ulysses, too, showed us what the solar wind looked like out of the plane of the ecliptic. At sunspot minimum, we saw that at high latitudes, you had fast solar wind, and at low latitudes, you had slow solar wind. But then also at sunspot maximum, everything was irregular. You had a complete mixture of fast and slow solar wind all the time. It was much more sporadic. At Hinode also, there's this important discovery of very strong outflows from active regions, completely unexpected. And these contribute, I'm not sure what the percentage is, maybe 10% to the solar wind. In future, though, I think we need much more detailed work on mechanisms for accelerating both the fast solar wind and the slow solar wind. There are a number of ideas around at the moment. For the fast solar wind, alphane wave acceleration is the preferred mechanism at the moment, and for the slow solar wind, reconnection is the preferred mechanism. But these need to be worked out in a lot more detail. And we need an in-depth plasma physics analysis in doing that. Clearly, out in the high corona, non-fluid effects are absolutely crucial. Then we turn to solar flares and coronal mass ejections, a small topic. In 1966, we were very happy about flares. A flare was defined as a brightening in H alpha, right? Coronal mass ejections had not been born. They didn't exist. Now we know that from a comparison between observations and theory that some solar flares occur at separators, and some solar flares occur at quasi-separatrix layers. There seem to be these two possibilities. The two main questions that MHD has to address are when you have an eruptive solar flare, what is the cause of the eruption? That's the first major question. And the second major question is, what is the nature of the reconnection process in the flare? Now, as far as the eruptive instability is concerned, there are several possibilities that have been put forward. Either a kink instability, or a non-equilibrium, a catastrophe, or a torus instability, or a breakout. But these are all very simplified models, simplified possibilities. In future, we need to develop much more realistic models for eruptions, and we need clues from the observations as to which directions to go. And in addition, we need the details of the three-dimensional reconnection process. So far, most of the flare theory is talking about two-dimensional reconnection, which is not appropriate. Three-dimensional reconnection, we've discovered, is completely different from two-dimensional reconnection. So, that is a kind of whirlwind tour of solar MHD, in which I've tried to highlight the effects that I think are important. It's clear that solar MHD has blossomed over these past 46 years. It's at the moment a vibrant subject. It's full of excitement. There's been a real revolution since the 60s. The major questions about dynamo, sunspot, solar wind, prominences, coronal heating, and solar flares, I think we've made major progress on each of these topics. Each of these topics has been refined. and the questions have been posed much more precisely, and also partial answers have been given. I think we've solved now the overall nature of two of these, the overall nature of sunspots and the overall nature of prominences. But as I've tried to mention, there are major questions, sub-questions that arise, for example, about the fine-scale structure of prominences. In future, what we need are cleverly designed numerical experiments by theorists that are closely in touch with observations, so that they're designing appropriate numerical experiments and are answering the right questions, answering questions and posing questions to the observers which can be answered. And we need the involvement of the IAC in major solar instruments and missions that are going to be coming up over the next decade. This is really important. But in the meantime, let's enjoy the sun. Thank you.
Okay, thank you for this very nice talk. So now time for questions.
I'm not a solar physicist, and I have a comment and a question. My comment is, very many thanks for telling me what all my solar physics colleagues are doing. It's been very instructive. And I speak without the trace of irony. I'm very happy about that. And the question is, how well do theorists understand the 11-year, 22-year magnetic cycle and phenomena such as the Maunder minimum and so on? I know you haven't dealt with this, but it's something which, as an outsider, I'm very interested in.
Yes, that's a very important question. I think there are qualitative ideas, I would say, around, but until we really have a well-developed dynamo theory, we will not understand the solar cycle properly. So there were theories of the solar cycle, on the basis of mean field theory, for example, assuming that the dynamo was operating throughout the whole convection zone. But we now know that those models are not appropriate. So as far as the solar cycle is concerned, I think we have qualitative ideas as to why the sun's magnetic field reverses, but why it's 11 years rather than any other period, I don't think we can say that for sure. In other words, we don't understand the solar dynamo well enough to be able to extrapolate it to other astrophysical environments, and therefore to be able to to understand stellar cycles, for example, properly. I think until we do understand the solar dynamo theory, any attempt to set up models for stellar cycles or galactic dynamos, that kind of thing, I think is bound to be qualitative and is bound to be potentially wrong. So I think a lot more work needs to be done in developing these models. The Maunder minimum is a big mystery. There are very simple models based on nonlinear dynamics theory, for example, which give you clues as to how a dynamo can suddenly go from being periodic to switching off. But these are very crude models. So I don't think we understand that properly. Although it's intriguing that it looks as if in the Maunder minimum, the dynamo didn't switch off completely and then start again. Because when you compare before to after, it looks as if the sun knew about the phase of the dynamo. In other words, it looks to me as if what happened was that the dynamo reduced its amplitude to a lower level so that it wasn't generating enough flux to be able to be emerging as sunspots. Right? So my own suspicion is that the dynamo was continuing to work, but it was working at a lower level. But that's very important to try and the solar cycle is a key question. I agree.
So I think at the beginning of the talk, you said that there is another solar physics institute in the world that is as good as ours. So I think I will invite you to give this talk with all our pictures there, or no matter what institute is that. Well, I'm just
well, I think the other Solar Physics Institute is either Lindo or HAO. That's my view.
Yeah,
but
just kidding.
Which one, you know?
Well, thank you for this overview. I mean, it's clear that you are familiar with all the work we've been doing, so I have enjoyed your talk very much. And thank you for the whole global view. Your global view, you've shown that is kind of separated, and I want to know if you believe there is a real separation between these two topics or not. And this is probably a bias that I have from interacting with the solar orbiter community. I do interact with all these in situ people a lot these days. There, what I have learned is that the coronal heating problem and the solar wind initiation is pretty much the same problem, because if you accelerate the solar wind, it's because you are heating the atmosphere one way or another. So if you solve one, you probably solve the other. And that's the impression most of these in situ people are transferring to me when I interact with them. So in your global view, they were like separated. Do you think they are really separated, or are they linked or not, these two problems, coronal heating and solar wind? All kinds of solar wind, slow, fast.
I made the point that I think there may well be different mechanisms dominating in different parts of the solar atmosphere. Now, I think the mechanism taking place in active regions and low down in the solar atmosphere may well be different from the mechanism that's taking place in the high corona. I think the mechanism that's taking place in the high corona is probably intimately related to the acceleration problem, to the solar wind acceleration problem. And I think, you know, what we really need, and it's one of the things that, what's his name? When you're over 30, your memory is not so good. You will discover this, Valentin. Cranmer, Steve Cranmer, that's one of the points that Steve Cranmer makes, that when you look at solar coronal heating models for the outer corona, then you also need to worry, you know, the two are the same. And I would agree with him. I think there is an overlap there, but I don't think there's an overlap necessarily low down. So that's why I think you need a variety of different approaches. I mean, certainly when you're high up, you must put in the detailed kinetic plasma physics, right? Which you don't need to in quite so much detail when you're low down, where MHD is more valid.
More questions?
So, in recent years, there appears to be evidence that coronal holes rotate rigidly, and so there is continuous reconnection of the boundaries of coronal holes with the local field they encounter, and that may have may be of importance for the acceleration of solar wind. Do you have any comments on that?
I would doubt that was sufficient to be accelerating the solar wind. I mean, if you have a large coronal hole, you know, the center of the coronal hole is so far away from the boundaries. I mean, I think that may be that aspect may be important, maybe giving you some acceleration, and that's why I think what we really need are quantitative mechanisms, you know, so that we can compare quantitatively the different ideas. I mean, there's no shortage of ideas now around for accelerating the solar wind and for heating the corona. Theorists have been really active and imaginative in coming up with different ideas, but what we really need to do is to make them more quantitative so that we can compare them properly. And I think that idea, you know, that may be giving you a small amount, but I doubt if it would be providing, you know, all the acceleration and heating that you need. Yeah.
Okay, so
there's one at the back there.
Question.
Let me see if I can explain myself correctly, which is not easy. My understanding of your talk is that you put MHD as the core of all the successes in solar physics in the last 40, 50 years. And Well, more or less, you put the equations when you started, but you started citing some things like Lena's effort to show or to prove if there is any multifluid MHD that would separate ions and neutrals and things like that, and that could be somehow breaking the old MHD that has given us so many successes. So how long MHD single fluid is going to last in the sun?
Okay, so I mean, I certainly confess that I have just been looking at the MHD of the sun, and there are many other topics in solar physics, you know, which I've not covered, and about which I know very little. So I've tried to focus on the areas that I know best on the MHD. I fully admit that, and also it's quite clear that we. In my book that I'm rewriting at the moment, one of the main points that I'm making is that it is important in future to go beyond single fluid MHD, to develop multi-fluid MHD, to develop kinetic approaches. There are a whole range of, I gave a review talk last year actually in Germany where I was describing, well the title was Beyond Fluid MHD. Right, and so I was trying to summarize the different ways in which you could go beyond single fluid MHD. And it's very important to do that. It's more complex. But I still think that single fluid MHD is going to remain a valuable model. You know, it's the whole theory, it's the whole philosophy of mathematical modeling. You start off with simple mathematical models. And if this seems to fit qualitatively with the observations, then you can refine them. You can make the models more sophisticated. You can add in extra effects. You can bring in multi-fluid effects and so on. You know, but the real question would be, you know, for coronal heating, for example, would you still get coronal heating in a single fluid MHD world? Or is multi-fluid MHD absolutely essential in order to get coronal heating? Or does it just change quantitatively the amount of coronal heating you get? Or does it change the details of the structures where the heating is going on? Right? I'm reminded of shock theory, for example, simple shock theory, where you know, you'll have a fluid coming in from one side, then meeting a shock, and then going out to the other side. The details of what's going on inside the shock are incredibly complex, but you can still relate what's going on one side, what's going on the other side from the conservation equations. So you don't need the details of what's going on inside in order to explain what's going on outside. And it may well be that there are examples where, you know, the MHD, single fluid MHD is giving you the global, the global nature of what's going on. But in order to really delve right in and understand the nature of the dissipation layer or the acceleration layer, that then you need to put in all these extra effects. You know, but the problem is the more you put in, if you go to kinetic theory straight away, then you can't deal with it. It's far too complicated, right? You can only deal with a minute region. You can say nothing about the global nature of what's going on. So I think you're always going to need these as complementary approaches to what's going on.
Okay, so any more questions? So if there is no more question, let's thank again to Professor Enrique.